I'm not going to go through any announcements today because obviously I've locked myself out, so I can't even give you announcements at this point, but we are going to go ahead and proceed on. We're getting ready to start chapter 4, and our chapter 4 is on forces. And so we're going to talk about forces, and now things are going to start to make sense or start to deal with a few other things that we've done before. So far what we've done is we've dealt with our triangle, and we've got the sine of the angle is going to be our opposite adjacent, hypotenuse is our opposite over our hypotenuse. Our cosine of the angle is the adjacent over the hypotenuse, and our tangent of the angle is going to give us our opposite over adjacent. We've dealt with vectors, so we can be in the r theta mode, where that's r and that's theta, or we can be in the x y mode. We have our equations of motion, which is my change in position is equal to my initial velocity times time plus 1/2 gravity times time squared, or acceleration. Usually we have a gravity or acceleration, so this one would be if I'm dealing with a y. I have my v final is equal to my v initial plus my acceleration times time. I have my v final squared is equal to my v initial squared plus 2 times my acceleration times my change in position. And we've talked about vectors being in the format of my x component in the I direction and my y component in the j direction, and that we have independent motion in our x and y and z directions. So that kind of gives you where we've gone. What we're going to do now is we're still going to be dealing with vectors, because force is a vector. And we have 2 types of forces. So let's kind of start with, we're going to play, we've got a group of folks over here, and we got a group of folks over here, and we've got a rope between them, and we're going to play tug of war. So this person is going to pull this direction, and this person is going to pull this direction. If the magnitude of the pulls is the same, then the flag doesn't move. The flag is going to stay right where it is. Now, if this pull, if the magnitude of this pull is 2 times this pull, the flag is going to move this direction. There's our direction. And we even know the magnitude of that pull. It's going to move at 1 time greater than that one. So we can look at these pulls, they're vectors. The pull is a vector. It has direction. And it has magnitude. So we are experiencing that change. So the sum of this, in this case, the sum of the pull, if I look at that from that perspective, it's going to be 2 pulls in that direction minus 1 pull in the other direction, and it's going to have the magnitude of whatever this person is pulling at. So we've experienced this, we've played this, we've done this in a variety of different ways. And that pull is something we call a force. And we've dealt with that before. Okay, we've dealt with that before. I have a box and I'm trying to get this box to move, and we apply a push to it. And if this box weighs 10 kilograms, we have a magnitude of a push in order to get it to move. But if this box weighs 20 kilograms, we know that push, this push has got to be greater than that push, because we've experienced it. So if I'm trying to get that 20 kilograms to move, or I'm trying to get that 10 kilograms to move, we get that push. And that idea, this idea that the more mass is going to require the greater push, gets us to this idea of inertia. The bigger the mass, the more inertia that we have. The bigger the mass, the more inertia that we have. So if I think of the push or pull is a force, one of the things that we know is that's going to be proportional to the mass. So my force, not farce, my force is proportional to the mass. So the bigger the mass, the bigger the force that I have to apply or I have to exert. I have more inertia. And we know this. I mean, this is one of those things that if we ever watch the Strongest Man competition, so let's think about the Strongest Man competition out there. And we've got this strong man is going to pull this. The hardest part of the pull is to get it started. So the hardest part of the pull is to get it started. And then once I get it started, it's going to be a lot easier to pull. Or I can push it. Now, pushes or pulls, we call those contact forces. And contact forces, think about it in that we are actually in contact with the object that we're using, or the object that we're playing with, or the mass that we're playing with. Those are contact forces. But we have another kind of force as well. So let's think of our box on the table. I drew a bad table today. We're going to have a fancy table. We're going to make it kind of a butcher block table. So I have a mass on my table here. And we know that there's something that's holding that mass up, because if we pulled the table out, the mass is going to fall. So if I didn't have that table there, we know that my mass is going to fall. Now, what we've known before is that I could have half this box and it would still fall. And the distance that it falls, the time that it takes to fall, none of that is dependent on mass. We don't have, mass is not the issue that we have. Mass does not apply. So it didn't matter when we were dropping the tennis ball, we were dropping the golf ball, we're dropping the bowling ball. None of that mattered with our mass here. Mass did not apply. But we know that the golf ball and the bowling ball and the tennis ball, something else is out there, and that's our idea of weight. And weight is going to be mass times my acceleration due to gravity. And if I think about my Earth here, if I have an object on Earth, there's always something that's pulling it down. It's experiencing an acceleration. And that experienced acceleration, or whatever I'm dealing with, results in the weight, and my weight is a force. And it has direction. It's going towards the center of the Earth. My weight is a force, but I can actually represent gravity as a field. So we can represent gravity as a field. So gravity is something that we call, or gives us, a field force. So it doesn't really have a string pulling on it. It doesn't really have anything else there, but it is absolutely a force that we have to deal with. And so we have field forces. But we're going to start looking at, and we're going to work with, for right now, we're going to work with our contact forces. Now let's think about some other things that we have. Even before I get us into Newton's laws, we want to talk about things that are happening. So let's go back to our strongman truck. We got our strong man over here, or our strong person. It doesn't have to be a man, it could be a person, could be a horse even. We got our strong man truck. And if I'm on a smooth surface, it's going to be a little easier to get that truck moving. If I'm on a jagged surface, it's going to be harder to get that truck moving. And in fact, we already know that if I'm on a smooth surface, it's harder for me to walk across the floor than if I'm on a concrete surface. And that gives us our properties, and this relates to a physical property. And our property is, we're going to call it a coefficient of friction. And my coefficient of friction is going to be dependent on the characteristic of my properties. Okay. And that's going to be, it's going to give me something that's going to resist movement, because what's happening here is I'm actually applying a force. And I have two types of friction. I have static friction, and I have kinetic. So if we're playing with our strongman again, we know the hardest time to get this thing to moving is right at the beginning, and that's related to my static friction. And once it's moving, it's a lot easier because my kinetic friction. And what happens is my coefficients of static friction are generally greater than my coefficients of kinetic friction. And we actually represent, and these things come in tables. Those things come in tables. We also have something else, and we're gonna bring this one out. And again, I'm just introducing it, and we're gonna come back to it, but I want you to have this information so that as you're starting your homework, which I should be able to get to in a little bit here, I have a spring, and if I pull this spring out, the spring is always going to want to have a restoring force. Or I can also look at the spring as a different way. I can push my object on my spring. I can push this and compress it. So this one would give me a stretch. This gives me a compression. But either way, I get a restoring force that wants to go back to its original shape. And that's my restoring force that's going to want to have that spring to go back to its original shape. And in fact, we're going to play with this later on in one of the labs, and we can actually look at it from hanging down, for example. And I can look at this stretch, and the stretch is going to be defined as our new length minus the original length. That gives us our stretch. I have the weight of my mass at the bottom. So this is my weight. And we're going to get something called Hooke's law. And Hooke's law tells me that I have a force is equal to a negative K X, where this is the stretch. And this is my force. And this is my spring constant. And this spring constant is dependent on the characteristics of the spring. So think about that. Let's see, I probably have one around here. So let's look at this. So I'm going to open up this pin. So that spring, we know that spring is going to have very big different characteristics than, say, a big spring in my around my shock absorber in my car. Those two springs, they could be made of the exact same material, but the number of turns, the diameter, the thickness of the wire, all of that is going to be highly dependent on what my spring is. But when we look at this, we know if I play with a spring and I compress that spring, we can actually feel the fact that I have to apply a force in order for that spring to be there. But as soon as I let go, it's going to want to return to its original shape. So we know that there's a force at play, and that is a restoring force associated with a spring. And we'll go over this a little bit more, but I wanted to make sure that you all had, when we're talking about different types of forces, we bring in the forces that we're going to play with. So our types of forces that we have, and we've discussed so far, we have our types of forces. We have our contact forces, which are going to be our pushes and pulls. We have a field force, which is going to be like gravity. And for those of you that have to take physics 2, we're going to find out that this is also electric and magnetic. We'll have those down the way. So I will have that type of a force. We have forces that are related to friction. And we have our spring forces, which is a restoring force. Related to Hooke's law. So that gives us our types of forces. All right. So we're going to go over some observations. And I like to do this a little differently than our book does. But we know a few things that are out there, and we will actually classify them as we're going. So I'm on the space station, because this is the easiest way to deal with it. I'm on the space station, and I'm going to toss a ball to my partner. And if I toss the ball to my partner, the ball is just going to keep going until something happens. Until my partner catches the ball, until the ball hits a wall, until a ball does something along the way. This ball is just going to continue to float on forever and ever and ever. We've seen that if I'm on an air hockey table and my puck is moving. My puck is just going to continue on. And if everything's perfect, it's going to continue on until it hits a wall or somebody puts a hand out to stop it. So the first observation is that an object in motion or at rest will remain in motion or at rest unless acted upon by another force. Or unless acted upon by another force, or we can mark through that an imbalanced force. So we usually hear this as that an object in motion will remain in motion unless acted upon by another force. But we really mean an imbalanced force. So if we go back to our tug of war scenario, where we have this person is pulling at a force, and this purse is pulling at a force, and the flag is in the middle, if that force, the magnitude of that force is equal to the magnitude of this force, that object isn't going to move. That's our tug of war stalemate. We have the same thing here if I'm dealing with my tabletop. And I have my object, which is a box. This box has a force that's pulling it down, its weight, but it's not moving, so I have some sort of force that is counteracting it. Okay, and that's on my table. This is my tabletop. This gets us the idea from Newton's third law, or a third observation. So we're going to call it our third observation. Yes, I know I've skipped the second observation because I don't like doing the second observation second. I like doing the second observation last. My third observation is that forces come in pairs. Or I have, if I'm at rest, I have equal but opposite forces. So at my tabletop or at the ground, so I have my object sitting on the ground. It's got the weight due to gravity that's pulling it down, which we've already said is mass times acceleration, or mass times gravity. But I have this opposite force, or the ground is pushing up on my object. And we're going to use this as our reference point. And that reference point is the center of mass. Or we can think of all the mass working with it. And this we're going to call our normal force. We're going to use an N to represent that normal force. But our third observation says we can calculate that, just like we can calculate this, that the normal force has got to equal the weight so that the object doesn't move. And this is, and I'm going to say this is specific just to remind us, because we're going to see some things in a second, that this is specific to this situation. Because I don't want you to get confused when we get ready to do something else. So my first observation is that an object in motion remains in motion unless acted upon by an unbalanced force, and that I have forces come in pairs. So we're going to work with that for a second. I did. Okay, so we're on an ice hockey rink. Okay, we're on an ice hockey rink, and I'm going to apply a force. And I'm going to apply this force here. And then I've got my counter partner is going to apply the force from this direction. And it's going to be twice the force. And we're going to have an angle here. And we're going to say that that's 45 degrees. We want to know, where does this object go? How is this going to move? or we're asking what is the resultant force. That's really what we're asking. So I've got my vector 1 is equal to the force in the I direction. My vector 2 is equal to my 2 times the force, and that's going to be cosine of 45 degrees. And it's in the negative direction because it's going that way, right? That force is going that way in the I direction. And this one is negative 2 times the force, sine of 45 degrees in the J direction. I'm going to end up with my resultant vector is going to equal force minus 2 force cosine 45 degrees in the I direction minus 2 times the force sine of 45 degrees in the J direction. Or I'm going to have the force, and then my vector is going to be 1 minus 2 cosine 45 degrees in the I direction minus 2 sine 45 degrees in the J direction. And so we can figure that out. And I'm going to have my force is going to equal minus 0.414 in the I direction, minus 1.4 1.14 in the J direction. So I drew my picture wrong. So that's what's going to tell me I drew my picture wrong. The magnitude of my resultant vector is going to equal the square root of, I've got negative 0.414 squared times force squared minus or plus a negative 1.414 squared force squared. So I'm going to have force comes out, so that makes life easier. This is going to be 1.47 times the force is going to be the magnitude that it's going to shoot off. But now we want to look at our angle. So the tangent is going to equal our negative 1.414 times force divided by our 0.414 times force. So my angle is going to equal a 73.7 degrees, but we find out that this is actually the actual resultant force is in this direction. And that's going to be our angle. So we have to deal with it. So that's our real resultant force. So we can play with our forces like vectors, just like we have before. Okay. Let's get to the second observation. The second observation is that Newton says, for the second law, and I'm going to write it out the way our book has it written out. Give me a second. So the second law, or the second observation, is that the acceleration of the object is directly proportional to the net force acting on it and inversely proportional to its mass. Which basically says this, that the net force divided by the mass is equal to acceleration. That's basically what it's telling us. That's not really Newton's second law. That's not what he actually observed. Actually, what he said was, he said that an impulse is equal to a change in momentum. So this is a simplified way of looking at this. Now, an impulse, and this will make sense, an impulse is I'm going to apply a force over an instant of time. So let's think about my hockey puck. I'm going to do a tap, and that tap is going to have a magnitude, my force. It's got direction, which is coming from my force. But how long I'm in contact with the ball, that little change in time, if this is at rest, we know what's going to happen. If I tap that ball, it's going to shoot off. And now it's going to have a velocity, just like what we saw early on. It still has its mass. It still has its mass. Now, momentum, we define momentum as mass times its velocity. And we use that a lot. Think of if I'm washing dishes with the faucet draining, or I'm washing dishes with the sprayer, because I got the same amount of water coming over the same amount of time, but it emits finer stream. I have to increase the velocity in order for that to happen. So we get this. So what we have is that my force, my impulse, which we're going to see come later when we start dealing with momentum, but I want to introduce it now because it's going to make this understand that this is a special case. This is the most common case, but it's a special case. So this is a change in momentum. So we get, this is also the second observation. Now let's look at this a little differently. So I've got my force is equal to my change in, so let's look at this. We're going to rearrange that. And so now my force is equal to a change in momentum over a change in time. Now, mathematically, we can play with this a little bit. And mathematically, what this looks like is this would actually equal my velocity times a change in mass over a change in time, plus my mass and a change in velocity over a change in time. All right, so I still have velocity, I still have this. Now we know what this is, right? We've seen this before, or we've seen this part before. This is the part we've seen before. We know what that equals acceleration. So force is actually equal to mass times acceleration, but I have this other weird term over here. I have that other weird term over here. Now, if I've got the ball, I'm dealing with this. I've applied the tap over an instant of time. I still have the mass. It's going at a velocity. There is no change in mass. The mass is equal to 0. So if I'm dealing with my ball scenario, there's no change in mass. So this term goes away. And I'm left with that my force is equal to mass times acceleration, which is equal to this special case. And that special case is the more common case, because if I redo this, this is net force is equal to mass times acceleration. So I get this part here. Now, when do I have to worry about this term? That's rocket science. Because if I'm dealing with a space shuttle, as I am moving up, I'm losing a lot of fuel, and I do have a change in mass. And I have to account for that. But for most of the things that we're going to play with, I don't have to account for that. But I hate giving you this particular definition without explaining that I have this here, because that's where we deal with rockets. That's where we deal with a lot of other things. And for you biologists, you know, this term may come into play if I'm consuming fuel for something, or I'm shedding mass to have something happen. This gives me my mass shedding term that I can still apply Newton's law, and Newton's law still applies. That's the thing that everybody doesn't get, is that this is a simplification of Newton's law. It's a total simplification. So we will see this again, but I like to bring this out to show you that I do have that force, and I play with that force. So it's very important that that's in there. So now we have our 3 observations. First is an object in motion. And then our second is that our net force is equal to mass times acceleration. And our third is forces come in pairs. Now, we also have another special case. Or you could say it's the bigger case, because it actually gets us back there, is that my force due to gravity is going to be this big G, which is constant, which is Newton's gravitational constant, times the mass of one object, the mass of two objects over the radius of the objects separated squared. So remember, Newton was trying, and this is where we get back into the history, is where all this comes from and why we start looking at this is because we were at the time, we're sitting here from Earth, and we've got a telescope, and we are watching planetary bodies. So we've got planetary bodies that we're watching. So we've got good old Mercury, and we have Venus, and we have Mars out here. And we were just now figuring out that, hey, the sun is our center and Mercury is going to go here. And Venus is going to go here. And Earth is going to come over here. And we got Mars out here. Those are the ones that are easy to see. But if I'm observing these planets from Earth, I'm going to get some weird things that are happening. Because Earth has got a shorter route to go around the sun than Mars, sometimes Mars looks like this in the night sky. Mars looks like it does a loop because I'm observing it from Earth. As Earth passes Mars, it's going to look like Mars is here, Mars is here. Oops, Mars is now here. And now Mars looks like it goes behind. And this is what we call retrograde. And our astronomer friends were trying to understand this. And so that's where we get Kepler and Kepler's laws. We come up with Kepler's laws, and Kepler has 3 laws. The first law for Kepler is that the sun, or all orbits, are ellipses. All orbits are ellipses around the sun, with the sun being at one foci. The second law deals with areas, sweeping of areas. And the third law deals with that my time, or the period, is roughly proportional to the radius squared. So Kepler's doing this. Newton is trying to look at these observations and explain the Earth-Moon system. So that's what Newton is doing. He's trying to deal with the Earth-Moon system. And so he's trying to come up with a way to explain these laws to look at the Earth-Moon system. And when he does that, we can rewrite this universal law of gravitation. And this gets us into our field force situation. So if I have one object, another object, and the radius squared, and this is along the radius because this comes from our field force. It comes from our field force. If I rewrite this, and I'm using my gravitational constants, and now I'm going to do the mass of the Earth, and now I'm going to do the mass of any object, and I'm over the radius of the Earth. So now I'm dealing with, I'm dropping a ball on the surface of the Earth. This distance here is much, much, much less than the radius of the Earth. I can rewrite this and get this value here, and this is my object that we're dropping, and this equals my acceleration due to gravity on Earth. And now my force for my object on Earth gives us our weight on Earth, which looks like my net force is equal to my mass times my acceleration, which is the common version of the second law. So this is the more formal version that deals with gravity. We can approximate it for our items here on Earth, which gives us our weight, which gets us back to our second law. And all of this was coming out from the fact that I was trying to explain what we're seeing from an astronomy basis. So historically, we come back here. We can actually talk about this one. This has got some really cool historical type stuff. Really cool observations. We'll come back on Friday when I can get you back in, because I want to show you Newton's laboratory manuals. We'll talk about Kepler. This is actually pretty cool because Kepler could be at the source of a conspiracy. So that could be a real cool one to look at as well. And we can play with that. But this gets us to this part. I want to do one more thing before we call it quits, because I have definitely given you all kinds of fun things today. But what we want to do is we want to talk about force diagrams. Because it's our force diagrams that are going to help us So I'm going to do, so physicists love inclined planes, and this is called an inclined plane. And so we're going to draw our force diagram on an inclined plane. So I have an object that's on an inclined plane. First thing that we want to do when we get our force diagrams is we want to draw the forces that are applying to the situation. So basically what I've done here, I'm going to use my tablet as my inclined plane. I'm going to put my calculator on here so you can see it. I'm actually raising it up. And right now, my calculator isn't moving. Now, the more angle I put to my inclined plane, eventually it's going to start to slide. Now, so what's holding my object there, at least at those lower angles, is a force due to friction. And so that's what I want to have keep this. So this particular mass, this mass is at rest. And I want to draw all my forces. So I have a force due to gravity, which is going towards the center of the Earth. I have a force that is perpendicular to my surface, and that gets me back to my normal force. So I have a normal force that's perpendicular to my surface. I have a force due to friction. And we generally are going to write our forces due to friction as a script F. So my script F is my force due to friction. My FG is my force due to gravity. And N is my normal force. Now, so those are the forces that are acting on my object. If my object is at rest, I'm in static equilibrium. And what that says is that my net forces have to equal 0. So we've got, for static equilibrium, my net forces have to equal 0. Now, the problem that we have is that my forces aren't in my same coordinate system. And so what we're going to end up having to do is we're going to end up having to put our force due to gravity into a coordinate system that makes sense for our inclined plane. And so what we're going to end up doing is we're going to break this force out in its 2 components. And this is going to be my force due to gravity perpendicular. And this one is going to be my force due to gravity parallel. You can go back to geometry and prove to yourself that these 2 angles are the same. So my force due to gravity parallel is going to equal my force due to gravity. The magnitude of my force due to gravity parallel is going to equal my force due to gravity sine of that angle. And my force due to gravity perpendicular is going to equal the force due to gravity cosine of that angle. And that's where I told you when we wanted to play with our opposites and our adjacents, is because when we get to situations like this, we're not in the XY plane, we're in some other weird plane, but we can shift that triangle all around. So we're going to have lots of force diagrams to play with, and I'll do one more because we're going to play with these too. So I'm going to have a sine. We're going to have a circle here, and we're going to hang it up from a ceiling, and we're going to use a rope or a chain to hold our sign up. And we want to know the tension in our ropes here. So I'm going to have my force due to gravity hanging down. I'm going to have my tension in this rope, and I'm going to have my tension in that rope. And we've drawn our forces that are applied. So we can start doing those forces that are applied. All right, I'm going to quit there today because I know I have given you all kinds of things to think about and introducing stuff. And I'll stick around for questions, and we'll go from there, and I'll see you